Thank you, Kelly. That was really just a wonderful way to start. And I'm thrilled that so many people are here. I realize it's raining, so not up against much competition. But let me do the following. What I want to do today, and just to give you a sense of my background, is it was fairly clear. I was trained as a mathematician, first at the University of Michigan and then at the University of Wisconsin. And I went on and got a PhD in decision sciences, which really meant game theory. And in the course of my work, what happened is I began to understand sort of the functional roles that diversity plays in systems. So what I want to do today, as hard as this may sound to do, but this is maybe the right crowd for it, is to try and have a little bit of fun and do a little bit of mathematics. But before we get there, what I want to do is I want to frame my talk. And I want to frame my talk by talking about diversity in two ways, because that's really what we're talking about this entire weekend. So the first thing we're talking about is the role of diversity in terms of interdisciplinarity. So if we take a pressing science problem, like the rising Earth temperatures, the way we go at this is by using a diversity of models. So when you think about this, one thing you can do is you can take sort of a standard carbon cycle model, such as the one you see here. And this might be taught in an ecology class or an earth science class. But in our physics classes, we might use a much simpler model. We might use just the simple pot of water model, right? Talk about energy coming in and energy going out. In economics classes, we would use what's called the DICE model, which is the dynamic model of the economy and the ecosystem going on at the same time. And each of these models is going to provide a different lens for what's causing global warming and how we can possibly intervene to reduce it. The second type of diversity I want to talk about is what we might think of as identity diversity. And one of the things, I think one of the challenges, and Kelly hinted at this, is if you look just down the pipeline a little ways, what you see is that American society is becoming incredibly diverse. Some people even refer to this as super diversity, in the sense that it's not just two races or three races, there's so many different ethnic groups and races, and we're all interacting in different ways. And the super diversity creates a lot of challenges, opportunities for us over the coming decade. But when we think about diversity, what I want to do, and if I get one thing across in this talk, I want to change how you think about diversity, particularly identity diversity, because often this gets framed in moral terms. It gets framed as the right thing to do. It's also sometimes framed in sort of defensive terms, like it's required by law, so therefore we're going to have policies that make us more diverse. And there's a sense in which a lot of universities and especially a lot of organizations think that one reason we want to be inclusive is because it enlarges the pool, right? It gives us a larger set of talent from which to choose from. The thing about those arguments, the thing about the moral argument, the legal argument, the larger pool argument, is that the diversity doesn't actually do anything. It's kind of multicolored sprinkles on top of the cake, but the cake is still ability. And what I want to do is I want to sort of change the frame. I think the current frame here, and I visit a lot of universities, a lot of organizations, a lot of government agencies, and what they do is they're sort of saying, we want to maximize excellence. We're currently ranked 14th, and we want to make the top 10. We're currently ranked 6th, we want to make the top 5. And we're trying to maximize excellence subject to this constraint that what we want to do is make sure we maintain certain levels of diversity. I think that's absolutely the wrong way to go. And I think instead what we have to recognize is that in order to achieve excellence in what we do, that has to stand on both a pillar of diversity and a pillar of interdisciplinarity. It's got to be the case that we're really tapping into all the skills that everyone has. To do that, what we have to do is we have to look inside people. We can't look at the surface of people. We have to look inside people and ask, what tools do they have? What experiences do they have? What perspectives do they have? How do they think about the world? And so when we think about identity diversity, what we need to do is we need to think about how that intersects with our cognitive differences, differences in how we represent problems, differences in ways in which we think about problems, different analogies we bring to problems, right? Because at the end of the day, the way we make progress as a society is by putting the different ways we think and reason to bear on common problems and on problems that we collectively decide are important. In doing this, and I think the key, I think Kelly hinted at this, what's so important is opportunity. So often when we talk about opportunity, what we think about is, wealthier children having, access to test preparation or slightly better schools. But it's deeper than that. So this is a graphic my younger son made for me yesterday, which is if you think about children that come from resource-rich environments, they can test lots of options. They can think about what's it like to be a biologist, what would it be like to be an engineer, what would it be like to be a physicist, what would it be like to be a basketball player, what would it be like to do fencing. And they can open up all those boxes and they can see which of these boxes really interest me, which of these is a gift that I can spend the rest of my life. People who come from resource-poor environments or people who live in places where they're not a lot allowed to contribute to things maybe only get to open one or two boxes. And if you only get to open one or two boxes, the odds that you find something that really motivates you, that really allows you to become exceptional, is much, much lower. And so when we think about this process of making STEM education inclusive, I think one of the things that's incredibly important is making sure that people get opportunities early on to be engaged. Because if you think about the probability of actually realizing that you're exceptional, that scales in an almost linear way with the number of opportunities you get. Okay, so that's a framing. Now let me talk about what I want to talk about. And that's this. I want to start off by talking about what I call a great big complex world. Because I think that's what we live in now, and we didn't used to live in that great big complex world. Then what I want to do is I want to talk a little bit about what I call the diversity bonus. So one of the things that you hear a lot about is there's this bonus from interdisciplinarity, or there's this bonus from having diverse groups. And I want to talk about that in a very serious mechanistic way. So I'm going to get rid of what I sometimes call the magic bonus argument, and I want to talk about where this bonus could come from. Then what I'm going to do is I'm going to show you with some very big data, huge numbers, right, to show that this diversity bonus actually exists. And then, borrowing from my Wisconsin experience, I'll talk for just a moment about how we might move forward. Okay, so let's talk about a great big complex world. What I mean is not the band A Great Big World, but I mean the fact that now the set of things you can know is enormous. So this is a picture of John Milton, and Milton was kind of an amazing guy because he supposedly knew almost everything, right? Now there's some people that say he only knew 84% of everything, but he was close to knowing everything, right? He read 20 languages, he wrote in 7 languages, right? And he read almost every book that existed. So if you plot all the books in print and you put Milton's, sort of year when he was in his prime, you realize there are about 40,000 books. So if you read 10 books a day for 10 years, you could pretty much get it all done, right? You could be Milton too. But if you were Milton today, you couldn't even read all the articles that came out in neuroscience last year. You could make it to June. So the point is, right, and this is the point, there's now so much to know, right, that any one of us only knows a tiny, tiny slice. So it's big. The other thing is, it's complex. So, as Kelly was saying, I've written 3 books. I wrote a book called Diversity, and then I wrote called The Difference, and then I wrote a book called Complexity, and then I wrote a book called Diversity and Complexity. And my son said, "So you're done now, right?" I said, "I'm done." But complexity basically means there's 2 sorts of definitions for complexity. One of them comes from Murray Gell-Mann, the physicist, which is that complexity is that thing that lies between order and randomness. So it's not so simple that it's ordered, but it's not so crazy that it's random. There's a whole other set of definitions that I call deep, and complexity are things that are difficult to explain, engineer, evolve, or predict. In other words, it's the sort of things that we try and do in the STEM disciplines. Now, what's interesting when we think about complexity, how do we cope with it? Well, one thing you can know, this is a graph by Jacob Foster at UCLA, and this is on a log scale. And this is research in chemistry. And what you can see is the number of authors, the number of chemicals, the number of things overall. This is in all chemistry papers published on JSTOR, is just going up over time. It's just becoming harder. If you look for evidence of this, this is a recent NRC report. 91% of all papers in the sciences, that's the red line, are now co-authored. 51% of papers in the social sciences are now co-authored. So the way we're coping with this complexity is dealing with things in teams. If you unpack this even further within the sciences, you see the modal paper in the sciences has 6 to 10 authors. So the idea of a single author, a single scientist sitting in her room, sitting in his room, cracking some hard problem, that really doesn't exist anymore, right? Science is now being done by teams. Now there's a recent report. Again, this is when I was talking about the NRC, where these graphs came from. And what they say is interesting is they say few, if any, serious research has been done on what allows interdisciplinary and multidisciplinary and diverse teams to be successful. And what's so exciting to me about this conference is this is exactly the kind of thing that the National Institute of Health, the NRC, the National Science Foundation, wants to see happen. We've got to figure out how is it that we make scientific teams, diverse scientific teams, better at what they do. Now, the conclusions of this report were twofold, right? And the first thing is that diversity is absolutely critical. The second thing is, when you put together teams, it has to be systematic. So one of the metaphors, the NIH had this big conference on this, and one of the metaphors was, it's kind of like cooking. You can't just take a whole bunch of diverse ingredients and throw it together and say, this should work fine, right? Because it probably won't. There has to be a systematic, mechanistic way of understanding why you think this particular group is going to work well together. Okay, so what I want to do is I want to talk about that. Because there's an adage within management, so I'm not a management professor, I don't even play one on TV, but in management, they always say, if you can measure it, you can manage it. But when we think about managing diverse groups, I don't even think we're there yet. I don't even think we even have a fundamental logic for what makes diverse groups work well. So before you can even measure it to manage it, I think what you have to do is understand how is it that diversity can work. So let me explain first what I call the magic bonus. There's a lot of people out there who would really like the following to be true. We'd like it to be the case that if I took two people who are different and I had them work together, that somehow magically the two of them together would be better. So like 80 plus 80 would give us 200. The thing is, that's not quite true. And the interesting thing is, if you look at the US economy 50 years ago, it wasn't true. So 50 years ago, 60 years ago, a big chunk of the US economy was involved in things like making washing machines, packing boxes, working in factories. And there's a whole field of research called time study or scientific management, where what they do is they would figure out exactly how someone should pack a box or how someone should put a rivet on. And if you look at the productivity of a firm, it literally was the sum of the productivities of each worker. So if I have people packing boxes, the total number of boxes packed by the 5 people, the boxes packed by the first, plus the second, plus the third, plus the fourth, plus the fifth. There's no bonus. There's no magic bonus. That's not the world we live in now. Amazon ships 306 boxes a second. One of my better students, Andrea Steves, got a job at Amazon. And when she got there, she's like, oh my God, you're not going to believe the job I got. And I'm like, what is it? She goes, we have to figure out what size boxes Amazon should have. Remember, they're shipping out 306 a second. So this took over a year to figure out how many size boxes they should have. And what's interesting about this is that this is a problem where there can be a diversity bonus. This is a problem where 1 plus 1 can equal 3. And so let me sort of explain why. This is an example of problem solving. So how do we think about problem solving? Well, if you ask psychologists how people solve problems, one thing they'll say is the first thing people do is they have some sort of perspective, which is a representation. Now here is kind of like, if there's a C.P. Snow moment in this talk, where there's a sort of the two cultures, the humanities and the sciences, this may be it. Go to any web page after this talk. Go to any preschool, go to Google, go to Ford, go to the U.S. Department of Education, any one of them. You're going to see somewhere on that web page that they say, we value diverse perspectives. We value diverse perspectives. And if you ask people who work at that company what that means, they'll say, that means we don't want the EEOC to come knocking on our door. That's what they think it means. So I've been down at NASA a bunch of times over the last couple of years, and for fun, when I'm down at NASA, I say, you guys value diverse perspectives, right? And they're like, right. And I'm like, exactly. Right? Because when you look at a point in space and you're at NASA, sometimes you use Cartesian coordinates, X and Y, and sometimes you use polar coordinates, R and theta. Those are two different perspectives. So here's the C.P. Snow moment. So on the one hand, when someone says we value diverse perspectives, this is seen as a political statement. But yet within a math department, within a computer science department, within an engineering department, if you say we value different bases for mathematical, we value different mathematical representations of problems, a scientist, a STEM person would look at you and say, of course we do. That's one of the ways we solve problems, right? It's through different representations. So this is something scientifically we understand, and yet it's somehow viewed through the wrong lens. Okay, so when you think about problem solving, perspectives matter. The other thing that matters are heuristics, algorithms, tools for solving problems. Okay? So here's actually how I got into this whole space. So when I finished my PhD, I got a job at Caltech, and I was teaching undergraduate economics. And I'm teaching undergraduate economics, and I'm using John Taylor's textbook. And in this textbook, he talks about people making airplanes. So I'm talking about people making airplanes and putting rivets in the planes. And one of the students goes, "This is totally irrelevant." They said, "We are not going to be putting rivets in planes. We're going to be designing planes, right? We're going to be designing fingerprint technology and computers. We're not going to be putting rivets anywhere." And I said, "It's a metaphor, right? Come on. It's an analogy. We're just kind of using this. It works the same way. Just like if I take the 5 people who can put in the most rivets or pack the most boxes, they're going to be the most valuable workers. If I take the 5 people who can solve the most problems and put them on a team, that team will solve the most problems." And then I thought, I wonder if that's true, right? So then what I did is I went home and I started writing some mathematical models and computer models. And in these models, what I did was I created agents. This is what economists call people. So these are like sort of mathematical representations of people. And they had these perspectives, which are representations of the problem. And then they had these heuristics, these tools for solving it. And then I could rank these people from smartest, right, from the best performers to the worst performers, right? And then what I did in this setting was I took a team of the very best problem solvers and a team of the very worst problem solvers. Now what's interesting here was when you do this, it turns out for collective problem solving, ability doesn't have very much meaning. I can take 2 people who have the same ability, and one person may add a lot to the group and another person may add very little to the group. The other thing that I did is I found that if I took a group of the very best, this was the thing that I'd found in class, I took the very best students, and I took another group that was just a diverse group, and then I had them work as a team, I expected the high ability group to work better, right? Now these are mathematical groups, but I expected this mathematical experiment to show me that the diverse group would do better. And my thinking here was as follows. I was thinking, okay, I'm taking one set of people who's really high ability, and I'm taking another set of people, some of whom are high ability, and some of whom are not, and the high ability group should be better than this diverse group. But the problem was that didn't happen. This is what, and for a while I called this a green eggs and ham result, because it was true on a tree, it was true on a plane, it was true on, no matter how I did it, it was true. But I couldn't figure out what was going on, so I brought in a friend of mine, Lou Hong, who's a mathematical economist, and she and I figured out, given the set of assumptions I was making, the diverse group was almost always going to do better. Now, the assumptions I was making that drove this result were the following. I was assuming people had tools. And here's the fundamental difference, and this gets back to the sort of thinking in terms of opportunities and boxes. The standard way we think about intelligence, and the way I'd been taught to model intelligence as an economist, was to use a measuring stick. To say, here's someone with an SAT score of 1580, here's someone with an SAT score of 1420. But in my models, I was representing people with tools, with skills, with experiences, with analogies, with ways of thinking about solving problems. Well, when you do that, what happens is the group of the individual best people on a particular problem will tend to have the same skills. So 2 weeks ago, I was at the New York Fed. And these are the people, the New York Fed claims to be the smartest Fed. Let's just leave it at that. And when I'm there, it's my people. It's 50-year-old white guys, and they all have the same tools as that group. They all have tool A, which is a PhD in economics. They all have tool B, which is a master's degree in mathematics. They all have tool C, which is a lot of training in econometrics. Some people have tool D, which is a little bit of knowledge of political institutions. Some have tool E, which is economic history, but that's about it. And you only have to think back about 6 or 7 years ago to see how well they did, right? So who's the other group? And you might be thinking, wow, is Scott trashing the state of Illinois here with the IL? And I guess I probably am trashing the state of Illinois. So who's the IL person here? Right? The IL person here might be someone who's a theoretical physicist who studies how to make robust networks. Now, would you want a theoretical physicist who studies robust networks to be managing your money supply? I would say no. And the reason why is they just like to be within a factor of 10. That's like their usual threshold. So I would say no. Now, but would you want to replace one of the cookie-cutter economists at the Fed with someone who knows something about constructing really robust networks? And the answer is, of course you would. Of course you would. And so when you think about dealing with these really complex problems that we deal with within the STEM disciplines, and a lot of the problems we face today, what you want to think about is tool diversity. You don't want to think about thermometer scores. And so what's happening here, the reason the diverse group was doing better is because they had different tools. Now, in order for this theorem to be true, this is a theorem that depends on conditions. There's 3 conditions that have to be met. The first one is what we call the calculus condition, which is that basically people know calculus. They can climb hills, right? So they can find places of zero derivative. The next one is the diversity condition. You've got to be drawing from a set of people who have lots of tools, right? And the third one, and the most important one probably, is that the problem's got to be hard. If you're packing boxes, if you're putting in rivets, then ability actually exists. But if the problem's incredibly hard, no one can solve it. And what you care about is the team. It's no longer about me, it's about us. This summer, I got this great opportunity to go to Cornell because a good friend of my wife's became president of Cornell, and she had me come there to talk to all of their deans about the importance of interdisciplinary research. I walk in, and John Kleinberg's sitting there, and John Kleinberg's he's a certified genius by the MacArthur Foundation, right? And John said to me, hey, by the way, I started looking at your results. I'm like, this should be good. And what he said, he goes, it's even stronger than what you think. It turns out, and this is how he says it in sort of computer science speak with supermodular functions and stuff like this, but what he says when you sort of translate this into sort of real English, this is work with one of his graduate students, is that unless the problem is separable, unless you're packing boxes or putting rivets in, there is no measure of ability. What does he mean? He means this. There is no test I could give people such that the highest performing people on that test would be the people that form the best group. There is no test. There is no test. The reason why is because it boils down to these differences in skills, right? It really boils down to the difference in skills. Okay, that's problem solving. Now let's do prediction. Problem solving is kind of heavy. Prediction's a lot more fun. The reason why is because prediction, people write popular books on prediction. So the first popular book on prediction was The Wisdom of Crowds by Jim Surowiecki, and he talked about fun things like cows. So he begins the book with the 1906 West of England Fat Stock and Poultry Exhibition. There's 787 people at this event, and they're all guessing the weight of this steer, and the steer weighs 1,198 pounds, and they're all making these guesses. Now, the average guess among these people was 1,197 pounds. So if you're an empiricist, at this point you can say, if we ever need to guess the weight of a steer, we'll get a crowd. If you're a theorist, you say, how could it be that the crowd could be this accurate? What you can do is you can prove something called the diversity prediction theorem, which says that the crowd error equals the average error minus diversity. Now, someone who's trained as a mathematician, when I say this is the diversity prediction theorem, this is a theorem. So last year, a school just to the south of Ann Arbor won some football championship in some division. I can't remember the details. But they had these bracelets that they wore that said O equals E plus M, which was something like output equals effort plus motivation. Okay, that is crap. That is like anti-STEM. That is not math. This is math. Okay? So when we say the crowd error equals average error minus diversity, we mean that kind of in a Pythagorean theorem sort of it's a mathematical identity kind of sense. Okay? So what do I mean by this? So the first term on the right, theta is the truth. If you take the crowd's prediction, which is C, and you take the difference between the crowd's prediction and the truth, that's the crowd's error. Now, it turns out you'd think that the crowd's error is kind of the average of the individual errors, and that's the second term. I'm just SI is each person's prediction. I'm just sort of averaging up, summing up, and averaging the individual errors. It turns out, and this is just a beautiful fact, that the crowd has a smaller error than the average person in it. And because of this beautiful fact, markets and democracies actually have a chance of working. If this were not true, markets and democracies would be horrible institutions. Right? Because they'd only be as good as the average person. But what this says, if you look at a market price, or you look at who we elect, it's actually a smarter choice than the average person would make, and the amount by which it is smarter depends on the diversity of the predictions. So if you take this back to Galton's data, what you get is that they're actually off by less than a pound. The average errors, these are 2956, these are squared errors. That means people are off by like 57, 58 pounds. So the important thing to keep in mind is these weren't cattle weight guessing savants or something, right? So these weren't people at the West of England who could just like go like this and like know the weight of a steer. They were no better than you or I. Cattle weigh like 5 times as much as people. If I get a couple pieces of pie in you, you could guess the weight of a steer within 50, 60 pounds, right? The reason I say pie is my wife got a job at Iowa, so we moved from Caltech to Iowa, and we bought cattle. And so we'd go to these cattle auctions, and you eat pie, and you guess their weight, and it's not too hard to get within 50, 60 pounds. That's the point. The reason that they were so accurate, though, is that they were diverse. Why were they diverse? The reason they were diverse is they probably knew the weight of their own steers. So this is a case of diverse experiences leading to a wise crowd. Okay, now, cattle probably aren't the most important scientific thing, so let's ramp this up just a tiny bit. So in 2006, we're jumping ahead 100 years here, Reed Hastings, who is the CEO of Netflix, had been reading about all this crowdsourcing stuff and wisdom of crowds, and he said, I wonder if I can just post a problem to the community at large, and they can come up with a better answer than I do. And the problem he posted was, they have this thing at Netflix called Cinematch. And so in Cinematch, when you type in a movie, it tells you how much you're going to like the movie. And so he said, if somebody can beat us by 10%, if you can be 10% more accurate than we are, we'll give you $1 million, right? Now, the way this works is, since I have 2 teenage sons, that if I type in a movie like Avatar, it's going to say 5 stars. You know, if you happen to only watch dark Swedish films or something, it may give you 1 star, right, for some science fiction thing. If anybody types in Rush Hour 3, 1 star, okay? So the idea was to try and figure out which movies sell. So there's 6 years of data, 18,000 movies, there's training sets, testing sets. This is done just like real science, okay? Everybody very quickly, after an early week, couple weeks of just some really crazy stuff out there, everybody boils down to having essentially the same type of model, which relies on something called singular value decomposition, which basically does this. You represent a movie by a giant vector. So it might be like attribute 1 might be, is it a drama? Attribute 2 might be, how many weeks was it in theaters? In some of these models, there was an attribute called Will Smith, Morgan Freeman. No, because it turns out they're not in any bad movies. This is one thing that came out of this study. Everybody else, even Meryl Streep, is in some bad movies. They are in no bad movies. So what you can do is it would then each person then gets represented by a vector as well. So if you like dramas, that's positive. If you like action movies, that's positive. If you don't like Nicole Kidman, that's negative. And then what happens is they match you to the movie and you make a prediction. So big boys and girls are playing in this. So the leader in this is Bellcore, right? This is the old Bell Labs. And Dr. Robert Bell, who's on the, I guess he's on the left in your picture, he's the lead guy on this. And originally they had 50 dimensions to their models. So that means for each movie they had 50 attributes, but they had 100 different models. And their best model could beat it by 6.8%. Now you got to get 10% to get the $1 million. Their best could beat it by 6.8, but when they combined their models, they could get to over 8%. Why, when they combined their models, could they get to 8%? Well, that's that diversity prediction theorem, right? They've got a whole bunch of diverse models, they combine them, they do fine. I can see all the mathematicians nodding their head, they're great. Okay, so here's what happens. Bellcore is winning for 2 years, but they're not at 10%. Dr. Bell, who it's worth, if you can get him to come to your university to give a talk, he's just absolutely amazing. So his boss comes into him and says, his boss has to genuflect because he's been leading this competition for years, and says, it's great that you're leading this competition, but you have this thing that we like to call here a job, and we would like you to go back to your job. And so Dr. Bell says, fine, I'll just win this thing. He cues the Rocky music and says, I'm going to win this thing. And his boss is like, pardon me, but you're doing this for 2 years, how are you going to win this thing? And he says, that'll be easy. I'm just going to call some people dumber than me. His boss is like, who would that be? And he's like, anyone. We know, we've pretty much established who's the best here over the last 2 years. That's not in doubt. I've just got to bring in some people not as good as me, and we'll be better than this. So what they do is they call in the team in second place. They don't call in the team in third and fourth place because they were doing things similar to the team in second place. But they bring in the team in fifth place, who are these Canadians. And the Canadians figured out better than anybody else when people had a life-changing event, like got a girlfriend, got a boyfriend, or had kids. It's like if out of nowhere you rent Blue's Clues, the other models were saying, bad choice. And the Canadians were like, they probably had a kid, right? So that sort of like Canadian insight allowed the best model to get to 8.4%, and now their ensemble of models got to 10%, so they win the $1 million. Except for they don't win the $1 million. And the reason they don't win the $1 million is the contest rules were very specific, and they said as soon as someone gets to 10%, the contest ends in 30 days. The reason they did this is they were afraid undergraduates who have access to supercomputers might beat them in the first week. In fact, undergraduates with access to supercomputers beat them by 5% in the first week. So this was a smart move, and now they're just going to have to wait 30 days. But Dr. Bell's reaction upon hearing that the contest was going to go for 30 more days was, oh, crap. And the reason it was oh crap is because here's what he knew. He knew there were 23 other teams from 30 countries that had been looking up at his name for the last 2 years. And he knew two things about them. He knew he was smarter than them, and he knew they were more diverse than him. And with 2 days to go, they beat him. And with 1 day to go, he beat them. And in the end, it comes out to be this like tie. But then it turned out Belcourt beat them on the 5th decimal point, but then it turned out the contest rules only go to 4 decimal points, and then it turned out that Belcourt submitted 22 minutes sooner, which was the tiebreaker, so New Jersey public schools got the money. That's the happy end of the story. But it gets better. It gets better because the ensemble had grad students, tons of grad students on their team. Whenever you got tons of grad students on your team, you can just turn that snarky knob all the way to 11, right? And so what the ensemble had on their webpage was they had this up there, and they said, it's official, Belcourt takes second. And they're absolutely positively right. Why? We have two models that are very different, that are equally good, so what has to be better? Yep, average the two models. Right? So Belcourt was second. So this is just a fundamental fact about prediction. Diversity is beneficial. Now this plays out in science. So this isn't just, not that movies aren't science, but this is a Goncalo Abecassis, one of my colleagues at the University of Michigan. He's a young star in the National Academy of Sciences already, fabulous scholar. Recently he got a grant, and it was an interesting grant because they said, we're going to have a horse race between Harvard, Michigan State, and Michigan to see who's best at identifying genes. So this is the Sanger Institute at Harvard, the Eli Broad Institute at Michigan State, and Goncalo's lab at Michigan. He wins. He's the winner, which is fantastic for him. And they have this, they all present their things up at this big meeting, and he's got the lowest error rate. He's all proud. And then the funding agent said, I've got an interesting idea. Why don't you have your 3 models vote? And that's the real winner. So if you look at this graph, this is the errors. The Michigan State graph is 3rd. The Harvard and Michigan graphs are very close, but the Michigan grad beats them, I'm told. And then the lower line, the dark blue line, which has the lowest error, is just having the 3 models vote. So the best way to identify these genes is not to rely on his best model, but to rely on the ensemble of models, right? Because diversity aids in prediction. Okay, so if this is true, if it's true that diverse groups of people are better at solving problems and diverse models are better at predicting, that should be evident in the data. Well, so Richard Freeman, who's an economist at Harvard, looked at this, and he looked at every single paper on the Web of Science. So this isn't, I sometimes tell my undergraduates, when you look at social science research, beware of what I call the Indiana coffee cup experiment, right? Where 30 undergraduates from Indiana played some game, and the winner's got a coffee cup, and now we're establishing that as some sort of empirical fact, okay? This isn't one of those studies. This is 2.5 million papers. What he finds, if you look at impact or citations, that number of past references, right, past citations has a positive influence. The number of email addresses has a positive influence. So if you just work with people from different universities, you get more citations and more impact. And he has this homophily measure. So what they did is they coded last names by ethnicity. If you work with people of different ethnicities than you get more citations and have more impact. So the essence of his article says, if you want to do B+ work with people who look like you from your home institution. Okay? Brian Uzi, as part of this NRC report, along with Ben Jones and some other colleagues, also looked at every single paper on the Web of Science and every single paper in JSTOR. And what they found, which is sort of amazing, they developed this test, what they called the home run test. A home run paper is a paper that has more than 100 citations. What they found is co-authored papers were 4.5 times as likely to be home runs as single-authored papers. So remember before I showed you like 90% of science papers are co-authored, and now it's over half of social science papers are co-authored? This is why. Co-authored papers are 4.5 times as likely to be big home runs. Now it's interesting, he also looked at what if you're from within the same university or from within different universities, and what you see here is these lines are all above 1 except for one exception which I won't talk about, and there you see the same effect. Working with people from other universities gives you more impact. Now the question was why? And you could say, well, it's just more authors so you can get more citations. So Brian dug into this in a deep way, and he found that it actually boils down to sort of looking at different pieces of information, like having different ideas. Now Melissa Schilling did the same thing, and her data is actually sort of, I think, more compelling because she just explains it, I think, more clearly. She did an odds ratio. So if an odds ratio is less than 1, that means it's bad, and if it's bigger than 1, that means it's good. So an odds ratio of 2 would mean it's twice as likely to be a home run. So what's interesting about her papers, she finds this. Remember I just said you're 4.5 times as likely to have a home run if it's co-authored? She finds an odds ratio on the number of authors to be 0.8. That means every time you add an author, you're 20% less likely to hit a home run. Now, I just said you're 4.5 times as likely to hit a home run if it's co-authored, but for each co-author, you're 20% less likely. The reason why is look at the things that have the giant numbers on them, the red numbers. The first one is depth, and that's basically they use the Dewey Decimal System to ask how many different disciplines are you drawing from. So if you double the number of disciplines, you're 3 times as likely to hit a home run. The last thing, this sort of novelty parameter, what she's finding there is this atypical combination, which is the same thing that Uzi finds in his work. If you cite papers or literatures together that have never been cited together in the past, you're 15 times as likely. So the 0.8 and the 15 and the 3 basically tell us this. The reason that team-authored papers get more citations is not because there are more authors. In fact, more authors hurt you. It's about having more ideas. But the problem is, if we go back to the great big complex world idea, no one has enough ideas in their head. So you pay a cost, and we'll talk about this in a second. You pay a cost by having a diverse team, by having more people. It's harder to do, but you get this enormous benefit, right? So you're paying a 20% cost and getting a 15-fold increase. That's the essence of her work. So how do we move forward? I think the first thing we do is we leave our silos, and I think this is, at the societal level, a really tricky thing to do. This is New York, and this is a racial map of New York, right? And what you see is the red regions are predominantly black, the blue regions are predominantly Caucasian, and the yellow regions are predominantly Hispanic. This is Detroit. That's 8 Mile. You could probably draw 8 Mile on that with a ruler pretty easily, right? Here's a middle school in Ohio. One of the green clusters is African American boys, the other green cluster is African American girls, one yellow cluster is Caucasian boys, the other yellow cluster is Caucasian girls. So what you see is a few friendships across gender, and a few friends across race, but you see these 4 clusters. Off to the right, you see 4 network theorists watching the whole thing from afar, right? These are the worlds we live in. This is the academic world we live in, right? You gotta love Google. You can type in silo house, and you get your choice of pictures. This was just my personal favorite. But it is the case you visit different universities and you just go visit the silos, right? And I think it's a mistake. These silos are no different than these silos and these silos. And it's a missed opportunity. The second thing is it's incredibly important to eradicate even small biases. So data like this shows up. This is Corinne's work where she shows this difference in you take 2 identical resumes, one of a woman, one of a male, and you get differences in rankings, and you get differences in salary offers. This is for postdocs. And if you look at these amounts, the amounts are small. And so it's so easy to say these are just small biases. But they're not small biases because what happens is if you think about all the promotions you have to take, this is like cutting the edges off a cube in higher dimensions. So if men are just 10% more likely to get promoted at each level, by the time you get to the 8th or 9th level, you've only got men left. So there is no such thing as a small bias. Small biases become big biases. I think the next thing that's super important about this, and Nancy Cantor will talk about this at length, I hope at the end of this conference, is what I call learning to ride the bike. So this summer I was at a maker fair in Detroit with my son. I had this bike that had an extra sprocket. And if you turn the wheel to the right, the handlebars to the right, the wheel went to the left. And there was a lot of people falling down, including myself. This was a hard thing to do. But I'm told if you work at this, eventually you can ride it just like a regular bike. There's a sense in which I think that's also true for diverse groups. So if you look at the data on diverse groups, you get the following picture. And let me explain this again by an analogy with respect to a bike. If I went out in a parking lot and took a whole bunch of 5-year-olds and had them run as far as they could in 10 seconds, I'd get a normal distribution with a mean of about 50 meters, and it'd be pretty tight, right? Everybody between about 40 and 60. If I put those same kids on bikes, the mean again would be about 50 meters. Some would go a long way, and then there'd also be carnage, right? That's why this is a thought experiment. This is not going by any human subjects committee anytime soon. If you look at literally 60 years of data on diverse groups, and whether that's identity diverse groups or training diverse groups or information diverse groups versus homogeneous groups, you see the same picture. The means are about the same. The very best groups are diverse, and the very worst groups are diverse. The reason the best groups are diverse, I think I've just shown you, right? You've got these huge advantages for solving problems, these huge advantages for making predictions. The reason diverse groups are the worst, we also know. It's because we haven't learned how to ride the bike. And so one of the things that's been going on over the last few years is research to try and figure out to what extent, what do we need to know how to do, and to what extent is this true? So one thing you can do is you can look again, this is big data, this is every patent ever issued by the United States government, and you can rank patents by how important they are based on basically how much money they bring in. And what you find there in this graph, the measure on this is proximity, which is how similar are the people who worked on the grant. And so what you find from these grants is the same thing actually you find from the papers, that the very best patents are made by diverse teams. They're made by low proximity teams. But you also find that the very worst patents are made by diverse teams. And it's because we haven't learned how to ride the bike. So here's some wonderful work by John Cummings and colleagues at Carnegie. He's at Duke and some colleagues at Carnegie Mellon. And what they do is they look across a bunch of papers and they want to see if you add more disciplines and you add more people, do you do better? And what you generally see is you see these increases. But what's interesting is when you unpack this, and this is probably a little bit too much data to sort of focus in on, but you see these there's a positive impact in terms of adding more authors and a positive impact for adding more institutions, but the interaction term between those things is negative. And what this suggests is we just still haven't figured out how to ride the bike completely, right? There's these big bonuses there, but we're still not tapping into it as well as we could. I think the last thing here is really, in a deep way, appreciating our differences. And I think this is where it gets very, very difficult. We still think of people, and I have 2 kids, and you talk about your kids in terms of their grades or their tests and those sort of things, and instead of really just embracing them in their fullness and thinking of all their skills and interests and talents. And yet when I think logically, or try to think logically about what's going to allow us to solve these really difficult scientific problems, it's going to be difference. It's going to be the fact that people learn different things and know different things and develop different tools. And so I think we really have to appreciate those differences. And this gets to the point I want to conclude on, which is, this is something I call the problem of problems, and I'm sure Nancy will beat this point home a lot on when she closes the conference. And that is, we have these precious universities. We have these amazing universities and colleges. And one of the mistakes we make is that the problems that those universities address are the things that we already decided upon. So my university at this very moment is having a giant diversity and inclusion initiative where we're trying to make our campus more welcome to everyone. Prior to that conversation, we decided to make a big move in big data, and we decided to make a big move in biology. But those big moves were made before we decided to be inclusive. And so there's a wonderful quote that I use all the time by Mary Oliver, which is, what do you plan to do with your one wild and precious life? And I think when we think about the direction of our universities and our colleges, I think we have to think, what do we plan to do? All of us, collectively, inclusively, the entire society. What do we plan to do with our colleges and universities? This is a decision that has to be made by all of us collectively in terms of how we spend our time and use our resources. And the goal of this is, if we have inclusive colleges and universities, if we really have communities where everybody gets to contribute, not only will we all contribute on solving what we think of as the current set of problems, but we'll also be involved in deciding on and solving the problem of problems. Namely, what is it that we're going to do with our wild and precious universities? Thank you very, very much. Any questions? Yeah. And we have I think we have microphones, is that right or not? Yes, we have microphones there and there. People have questions. Somebody's heading over, I think. There we go.
I don't have a question. I have a favor.
Okay.
Can we have a copy of your speech? That was so good, but I couldn't get it all down.
Okay.
And I work in groups. I teach in groups, and this was perfect for how groups work.
I think they have it taped, right? Is that correct or not? I don't know. Maybe somebody wrote it down really fast. Are there any stenographers? This is where we need a stenographer in the house. Other questions?
I was wondering if you could talk a little bit about the difference between working in a group and working in a team. So we do a lot of group work that students hate, and I know that there's some literature that distinguishes the two, but I'm not very familiar with it.
So how do you make the distinction?
I think for me, it's common motivation to an endpoint, and groups don't have that, but teams do.
Yeah, so I guess I would sort of define it the same way. I mean, it's one of the things that's interesting about the group team distinction. The reason I wanted to make sure we're on the same page here is that there's probably 30 to 40 years of research on diverse groups, and one of the things that comes out of those is that they come up with more solutions than homogeneous groups, but they don't necessarily come up with better answers. And there's two reasons for that, and you've kind of hit at one of them. One is that if people aren't quite sure where they're going, you can get more answers that maybe aren't headed in the right direction. The other thing is you run into what Barry Shorts calls sort of the paradox of choice. It becomes very difficult to evaluate among 40 or 50 choices, right? And so you're more likely to make a mistake. So there's a group I'm involved with called the Collective Intelligence Society, and it's a bunch of scholars that study everything from like bees and ant colonies to groups of people. And one of the things that comes out of that literature, which is really interesting, is if there exists an oracle, and by that I mean if there's something we can just go to and say, hey, how good is this solution? Then groups work really, really well. In that problem of like, hey, we're all focused on the same thing, it's less of a problem because I can just, like with the Netflix prize, I just put in my model, we hit the return key. If yours is better than mine, yours is better than mine. I talked to people at Ford Motor Company about this, and they were saying that when they design an engine, they have these perfect simulations. So they can have their summer interns play with like the shape of pistons, hit a button, and if it works better, it works better. So there's an oracle. And so they can have huge groups solving those things. When they design a dashboard, forget it. Right? There's no dashboard oracle. They can't like put the dashboard in the computer and hit a button. In fact, they joke that they have like people from, he goes, what are those things that people from New York have, like the little hair here? And I'm like, you mean a soul patch? He's like, yeah. People with soul patches come in and tell us what the dashboards are like, right? So they're very expensive oracles. And they also, because they're from New York, I guess. But the point is that if you don't have an oracle, that team group problem becomes very, very hard. Yeah. Yeah.
I was just wondering about when you break down silos, do your models get to the point where there isn't enough diversity to go back to draw from? Like, how does that figure into the model? So this is a great point. I think that one of the things Nancy Cantor is going to talk about on Sunday is a report that they issued, and in that she gives a citation. So it's in your program, the article, and if you go into that article, she'll mention a guy named Donald Campbell. And Campbell has a wonderful article on what he calls sort of the fish scale model of diversity. And the idea is that you've got people who are going deep, but they're kind of like fish scales and they overlap. And so what you need these fish scales in order for this interdisciplinary actually to work. So that was sort of the first, I think that was some of the first ideas in terms of thinking about the importance of making sure you can sort of translate across the disciplines and understand. It probably gets more full voice. There's a guy named Ronald Burt who's at the University of Chicago who talks about structural wholes and talks about people who can translate information across discipline.
And there's increasing evidence that people who fill these structural holes can have an advantage. And this is where, I mean, again, going back to that NRC report, it's not just a matter of saying, hey, let's have a diverse group, right? It really is, you've got to think about this in a systematic way. So Microsoft actually is working on something right now where they just bought a new company where they actually do tool-based accounting of all your employees. So every single employee will have like a giant vector, just like those movies. And the reason why, because increasingly a company will be like, they'll open up some Java code and it'll be written by someone who speaks Portuguese. Now you may say, wait a minute, is there really such a thing as Portuguese Java? And there is, because you just use Portuguese words in your Java code, right? And so you're like, do we know anyone who speaks Portuguese and knows Java? And the odds are you probably have someone in your firm, but you don't know it. And so by having these giant vectors of tools, you can find all those people. So one of the things I think that is going on within sort of human capital management and talent management is trying to embrace people in their fullness in terms of, you know, tools and badges and that sort of stuff. So then you can figure out, do we have someone who like understands biochemistry that knows a little bit of electrical engineering, right? And you can pull that person out of your firm or out of your organization, or out of your university to make it work. Another thing you can do, which Michigan did, is we had this a coffee program where you could just sign up for coffee, and then we had this mad computer scientist come up with a matching algorithm, and you would go to lunch, go to coffee with somebody who you might have research interest with, right? And then if it worked, it worked. It was kind of like speed interdisciplinary research. If it worked, it worked. If it didn't work, okay. All right, yeah. Maybe one more, and then we'll, between you guys and coffee. All right.
So thank you for your talk. I am intrigued and I resonate to the idea of forming teams to purposely create diversity, but I'm wondering if you could talk about either research or your perspectives on the idea that teams could also purposely find their diversity. So I think at times we get together with people and we think we aren't diverse when we actually do have diverse sort of background experiences to draw on, or teams that actually think that they're really diverse but need to find their commonality, which is a slightly different take, a less deterministic take and a more constructivist take.
Yeah, I think, so let me give sort of two answers to that. Is one is we're not really sure what types of diversity are relevant in what context, right? So if you think about, you know, to what, like there's a couple recent books, one by Doug Hofstadter on the role of analogy in problem solving. When something comes really hard, you can start pulling analogies from experience. Well, if that explains 30% of the variation or something, then different life experiences matter a lot, right? And you might also think, well, how you're trained may matter a lot. And you know, we saw this stuff on different schools. So I was at the Department of Justice had me in, and one of the things that they told me sort of before I got there is that they have this real sort of, the phrase they used was Yale fetish, that they really like people from Yale. So for fun, I took down the constitutional law syllabus from Yale, and then I looked at ones from Stanford and Kentucky and Alabama and Michigan, and it just picked like 15 random schools, and it was amazing how little overlap there was. So you could think like, wow, okay, we were both trained as lawyers, but if you went to different law schools, maybe you didn't learn the same stuff. And I was surprised when I was done at NASA, we pulled the electric, just for fun during a break, because this is what you do when you're at NASA, I guess. We pulled the electrical engineering majors from Georgia Tech, Michigan, Berkeley, Auburn, and one other school, and there was a lot of overlap, but there was also a lot of non-overlap. And you could realize, okay, wow, you could have, you know, two recently trained electrical engineers, and you could think from the same identity group and think they're exactly the same, and in fact, they might have learned completely different from completely different books with completely different focuses, and that difference could be meaningful. And so I think one of the things when we think about a problem, we have to ask, is this purely a mathematical problem? Is this a biological problem? How much does the problem depend on understanding the world? So as someone who works in social science, it's very difficult for me to imagine a meaningful social science problem where identity diversity doesn't play a role. You know, it always plays a role. And so if I'm in a room with all white guys, it just doesn't have the same look and feel. And then the second answer I'll give, and I realize this was long, is that there is recent evidence, it's not overwhelming, but there's growing recent evidence that if you're in a room with people who look different from you and were trained differently from you, you think of more things yourself. just because you're encountering that difference. And so when you encounter difference, you sort of are just forced to think about the world in different ways than you might have before. And I think that's one of the really sort of enlightening and enlarging things about diversifying our communities, right? Is that it's not only bringing more people in, but I think we're also enlarging ourselves. Right. Thank you very, very much. Oh, one more.
Thanks for your extraordinary remarks. We're here as agents of institutional change.
Right.
Can you give us some advice on how to incorporate your wisdom and rather than just working with students, how we can become more diverse in solving the problems?
So I think a lot of hiring within universities is done within silos, right? It's done within departments, and promotions are done within departments. So I think it's very important to think about, are you missing out on opportunities to hire people who maybe fit across more than one department? And I think it's also the case when you think about making tenure decisions. It's super important that you think about rewarding people who are making contributions to more than maybe just their home discipline. Yeah.
That was our last question.
That was it.
Yeah, please join me in thanking Dr. Page. Thank you very much, Scott. And I'd like to invite all of you to join us for our reception, which will be held right next door. But before you go, there was one thing that I forgot. I forgot to extend a special welcome to Dr. Brian Gilbert. I don't know if Dr. Gilbert is in the room. Hi, Brian. So Brian completed our evaluation survey last year and was then selected to receive a complimentary registration for himself and a colleague. And I should also congratulate Dr. Michael Palladino, who received an iPad mini for completing the evaluation last year. So we do encourage you to complete our evaluation survey, and we will have more details about that at the end or as the next day and a half unfolds. And finally, I am to remind you that Continental breakfast is free, and it will be served all over this hotel for you in front of every meeting space on every floor tomorrow morning and Saturday morning. If you are not able to find free food in the morning in this hotel, it's because you're just in the wrong conference hotel. Again, welcome to the STEM conference. Good evening.